Anyway, so you're in charge, Alan.
Yeah, because that's daunting, but thank you so much, TV, and to the IGS for having us. I think these IGS webinars are awesome, and I know that there's some time dedicated, like once per month, right, to focus on early career researchers. And when the call went out to say, hey, who wants to give talks, it was like, I know a group of early career researchers that would give some great talks. And that's this year's Juneau Icefield Research Program students. So I'm going to give a quick intro to the Juneau Icefield Research Program, if you haven't heard of it before. And then we'll have a series of presentations, each about 5 minutes or so long. We'll have time for a question or two right after each talk, and that should give us enough time. And then we'll see at the end if we have some wrap-up time for questions as well, just so everyone knows how this is going to go. So I'll share my screen right now, and if you can't see it, let me know. But the Juneau Icefield Research Program, or JERP, is something that a lot of glaciologists might have heard of, but if you haven't, the question starts at what the heck is JERP? Well, it's an expeditionary field education and research program on the Juneau Icefield in Tlingit Ani, or Tlingit lands, in Southeast Alaska, and it goes through a little bit of British Columbia and the Yukon as well. So it's an international program even though it's mostly the US. So how does it work? Well, students show up in Juneau on the south end of this map, spend a week or so there, starting to learn field safety skills, basic glaciology skills. It's open mainly to undergrads, but also advanced high school students and early grad students. Over the course of the next 6 to 8 weeks, they move across the ice field, first on foot, then on ski, moving between a series of set camps. And there's a mix of educational programming and research that happens along the way. And so students don't have to have any field experience or any particular, there are no particular prerequisites for students. And so we emphasize really a breadth of experience and a systems science approach to how the students learn along the way. And so you might hear some references to different camp numbers. Well, Juneau Icefield Research Program was started back, I guess 75 years ago now. This is our 75th anniversary. And the numbers at one point, I believe, were the order that the camps were founded in. And now they're mostly a relic, but they progressed from Camp 17 to Camp 10 to Camp 18. 10 and 18 are kind of the central icefield camps, and then across to 26 and end up on Atlin Lake before catching a boat to Atlin and coming back around to Alaska along the way. So what sorts of science get done? Obviously, a core of the Juneau Icefield Research Program is glaciology. That's why we're here at an IGS meeting. There's a long-term mass balance record that's kept for the Lemon Creek Glacier and the Taku Glacier, and a whole bunch of other glaciology research that happens on the Juneau Icefield each year. We've got atmospheric science and climatology that happens along a bunch of weather station data and other seasonal measurements that are done. We've got geology and geomorphology, both in terms of just understanding the coast range and glacial and geomorphological interactions that are happening. Polar engineering, testing out some new gear, different types of remote sensing, different types of drilling. It's a great platform for testing equipment out because it's relatively easy to operate on, and we have a lot of experience operating there. And it's certainly a heck of a lot easier to get to Southeast Alaska than it is to, say, Antarctica. And then also leadership and outdoor recreation. So students get a bunch of field experience, and also not just following the field safety staff, but getting experience in planning their own mini expeditions and things like that along the way. And we would be remiss if we didn't also talk about science communication. One of the things that we really emphasize among JERPers is that they talk about their science and share their science and share what happened over a great summer. And so these are a couple examples of drawings that got done by some JERP students in years past to illustrate their research projects. So I could spend the entire time just on a slideshow. I won't, but suffice to say there's some great science and some beautiful landscapes that happen up there. Over the course of the summer, the students get to do research projects working with faculty that come up. And so some research projects are really short, some are a little bit longer, but it's a capstone part of the Juneau Icefield Research Program student experience. In case you want to follow up more and with more questions, I would be remiss if I didn't mention the JERP leadership team. So we've got on the line today, Dr. Seth Campbell, who's our Director of Academics and Research, as well as Annie Boucher, who's our Program Manager. And then we've got Lindsay and Brad, who are the Associate Directors, and we've got a team of folks on our Academic Council that provide a little bit of, I guess, consulting experience and yeah, help with curriculum and planning as well from the academic side. And I'll also just say that the call for 2022 JERP is open right now. Student applications are open and will be given first consideration if they're submitted by the end of the year. So to all those other IGS folks on here who might have students that want to learn some more about glaciers, glacier systems, and get some awesome field experience in Southeast Alaska, please submit your applications, and applications will be opening up soon as well for other roles, including staff, teaching faculty, and research faculty. And if you're interested in doing your own fieldwork up on the Juneau Icefield, you can reach out about that as well. All that information is up on juneauicefield.org. So without further ado, I want to present our slate of talks that we have this evening, or morning, depending where you are. I want to emphasize that these student research projects, some of them have really cool results. Some of them raised more questions than they answered. Some of them gave null results. So we have a great, I guess, cross-section of what research really looks like as a field researcher, which I'm sure everyone can relate to. So this is the list. I won't read it out loud because you can read it, but I will say we are starting with the GPR team who are studying fern thickness. So I will stop sharing my screen so they can start sharing theirs.
Perfect, just one moment. There you go. Go ahead, Alex.
All right. So we want to take this opportunity to acknowledge that our research was conducted on the unceded territories of the Akwán on Tlingit Ani, also known as Juneau, Alaska. We acknowledge that the Tlingit peoples have been stewards of the land on which we work and reside since time immemorial, and we are grateful for that stewardship and incredible care. Gunash Chish. So our research looked at the change in fern thickness on the Mathis and Taku glaciers on the Juneau Icefield, which is in Southeast Alaska, between 2012 and 2021, using ground penetrating radar, which we will refer to as GPR. Unfortunately, one member of our team could not be with us to present today due to an academic commitment. That's Rachel. So why is fern important? Well, fern is an important component of glacier health, and it also has impacts on downstream local and regional linked systems. For one, fern eventually becomes the glacier ice itself. So a shrinking fern layer will have a negative impact on the growth of the glacier in future years. Fern also absorbs some meltwater that's flowing through the glacier, like a big sponge. So if the fern layer shrinks, then the sponge gets smaller and retains less water, so more water will flow out of the glacier system. This increased outflow will have a significant impact on downstream ecosystems, which might depend on a specific amount of water flowing out of the glacier system and will end up being damaged by this increased flow. Also, as a side note, more water flowing out of the glacier will eventually reach the ocean and feed sea level rise.
So how did we actually study the amount of fern on the Juneau Icefield? We did a temporal comparison between 2012 and 2021 by using ground penetrating radar towed behind snow machines. These radar units were towed at about 5 to 7 kilometers per hour, and the radar units were set to a frequency of 400 megahertz, which allowed us to both see all the way through the fern to the fern ice transition, as well as to see cool features in the fern itself, like fern aquifers and ice lenses. We GPS the transects between 2012 and 2021 so that we could use the same spatial comparison for all of the 150 kilometers of transects. The results of those transects are shown here. On the left, we have the 2012 figure, and on the right, we have the 2021 figure. The red shows less fern, and the blue shows more fern. So we'll talk a little bit more about what the results of this were later, but first we'll do a quick note on what is done to actually ground truth these GPR transects.
In order to ground truth our data, we used measurements from one shallow snow core and several mass balance pits that followed our transect along the Mathis and Taku glaciers and reached the fern layer. This provided us with an in-situ check for the fern depths that we found in our GPR data. We were then able to constrain our assumption for the dielectric constant, which was highly affected by both density and water content. We found our dielectric constant to fall between 2.1 and 2.6 after this step and also after distance normalizing the data, which made sense considering the snow conditions in this region of Alaska. This was an important step in calibrating our data to make sure our remote sensing values made sense.
So overall, we observed changes in fern thickness between a loss of 6 meters to an increase in 4 meters. On the Mathis Glacier, which is the top center of this figure over on the right, there was an increase in fern thickness at the higher elevation near the Mathis Llewellyn Ice Divide, while there was an increase in fern thickness moving down glacier. On most of the Taku Glacier, we observed a decrease in fern thickness. And this figure shows the fern thickness between, the change in fern thickness between 2012 and 2021, where the negative values in red indicated decrease in fern thickness, and the positive values in blue indicate an increase in fern thickness. And the black boxes represent the sites where we used for ground truthing.
All right, and then at this point, we can make a few preliminary conclusions. So first, that these changes that we're seeing in fern thickness across the Juneau Icefield will have implications for the Southeast Alaskan watersheds. Second, that this change in fern thickness between 2012 and 2021 is spatially complex. And so this indicates to us that there are likely interactions between multiple variables here at play, affecting where the fern is situated. And so, like Emily mentioned, with our calibration of our data with the relative permittivity values, those are really looking at the snow values that we calculated. And so that was between 2.6 and 2.1. Now, the real question that we're having to answer here, or the question that this has led us to, is what about the relative permittivity through the fern layer itself? Anyone who's been to the Juneau Icefield, as many people are here or have been here, knows that it's like very wet and a temperate environment. And so we know this affects the relative permittivity values that affect the radio wave velocity traveling through the material necessary to calculate fern thickness. And so this takes us to our future work, which will consist of using multi-offset radar, fern coring, and common midpoint surveys in order to constrain this value even more. And that's it for us. Any questions?
Thanks, team. That was great. And I realize I misspoke at the beginning. We want to make sure we have time for everyone. So if people have burning questions and you're not going to be able to stay for the questions at the end, please do put them in the chat and we'll answer them over text. Otherwise, we'll save questions for the very end so that we can make sure that we have time for everyone's talks. I'm sorry, I misspoke about that. But thank you so much for our GPR Fern team, and we'll move along to the AP Res team next. And while we're saying that, we'll just say that Team Climate should be on deck after them.
And is this in presenter? Like everyone could see this?
Yep, you're good.
Okay, great. All right, so I'm going to be talking today a little bit about the glacial hydrology investigation. This is right adjacent to Camp 10, right off the side of the Taku Glacier. I worked alongside a few other students, main students, that investigated the use of this autonomous phase-sensitive radar echo sounder, or otherwise known as AP Res. Also had help of some research faculty as well. So to start us off, just to get into the base of why we want to use AP-Res here. AP-Res is a frequency modulated continuous wave radar system. And basically it has had very little use in a temperate glacial environment. So we thought it'd be the Juneau Icefield would be an ideal location to test it out. Also, this North Basin area that we decided to deploy AP-Res in, past previous field seasons, there was observations of some concentric cracking, as you can see, and this is this year's picture from this year, as well as some blistering. And that might signify some filling and draining activity, possibly due to a lot of subglacial water storage. The idea is there's possibly some seasonal variability where there'd be some filling up from the cliff faces off of Taku B. That's an example of where liquid water, meltwater would come from, also through the surface. And then eventually you'd have some either outburst or just, evolution of the subglacial channel hydrology that would lead out the water and allow the more subsidence of the proposed subglacial lake. So this is just a quick radar gram from a sample in Antarctica, and shows where this water is where there's strong reflectivity due to the dielectric contrasts between the materials of water and ice. And so we were basically looking for something like that. So we initially decided to use GPR, 100 megahertz unit, as well as a 10 megahertz and 400 megahertz to get a wide spectrum of the englacial and subglacial geometry of the ice and snow. And so we basically used 100 megahertz to estimate where an ideal location for the AP-Res would be. And we chose an area that had an approximate bedrock depth of 245 meters. So setting up the AP-Res device, we have 2 antennas and then a central control box unit. The antennas are spaced around 30 or so feet apart, equal to each other from the central control box, which is autonomous. So we basically put in all the data for how the intervals of measurements we would take. And I also did some surface ablation measurements, and we had seemed around an average of around 30 centimeters of surface snow loss. So this is just an example of with the AP-Res device, what we were looking to possibly see. And so when we deployed this AP-Res, it was out for about 10 days. It took radar bursts every 15 minutes, and then there were around 100 chirps within that burst, and each chirp was around a second long. And we had a tonal sweep between 204 to 400 megahertz, which enables us to basically measure any type of phase shift that's due to a layer migration or material property changes where we'd see an amplitude change. And that phase shift is the scale is approximately, we can measure to around 1 centimeter accuracy for layer migration. Just getting into some preliminary results, still working on this project, but between the 10-day period from the start to the end, I just wanted to show a few little points that I had noticed that we might be possibly seeing some shifts in amplitude and phase shifts. So this first picture here, the image on towards the left, we can see that might be a strong amplitude change between the first and last day of the deployment. And then we'd see possibly in the next clip here, we can see a possible phase shift. Then moving over one more, it looks like there's more of a trend of not much change in that region of the depth. And then all the way towards the bottom around the 240-ish meter mark, we have a lot going on, and it looks like a mix of some phase and amplitude changes. So one challenge to deal with is we had around 960 bursts over the 10-day period. So we're trying to figure out a good way to average this data between seeing if there's any diurnal cycles, as well as just a general trend along the deployment period, and also how radar attenuation occurs with near surface water content changes. In this area, we actually had rainfall towards the end of the deployment period. So we might see more signal power loss due to attenuation more near the surface. So these are just some continuing things that I'm trying to work on, and hopefully we'll come across with seeing a little more detail of what occurred during this 10-day period.
Great, thank you so much, Team AP Res. Yes, claps. The climate team is up next, and I believe Team Isotope is on deck after them. So Team Climate, take it away.
Cool, let me share this. Okay, so hello everybody. We are the climate group from the 2021 JERP expedition. All of us are here present today except for Cole O'Shea-Levitt, who cannot be here. And for our project, we looked at the climatological patterns across the Juneau Icefield from 1985 to present. So this slide just shows the temperature and elevation of 6 camps that we used in our study. We used weather data collected from stations at these camps. On the left are drawings of each of the camps with elevation and temperature color listed, and on the right is a full map of the ice field with the camps listed on it. Previous work shows that winters here are warming at 4 times the global average, with no warming trend observed in the summers. This data inspired us to look at warming and the increase in glacial melt across the ice field. So our main question was, what are the trends in precipitation and temperature on the Juneau Icefield? And to investigate this, we looked at lapse rate, precipitation type, and ablation season length and intensity.
So for my part of the project, I evaluated how lapse rates across the ice field changed during our study period. These lapse rates are calculated by linearly regressing temperature with elevation at all of our weather stations. And an important distinction is that we're looking at surficial lapse rates here rather than free atmospheric lapse rates. And the primary difference between these two is that surficial lapse rates are much more sensitive to changes in microclimates. So on this plot, the average annual cycle for lapse rates is shown for the first decade, 1987 to 1997 in blue, and the last decade, 2008-2018 in orange. On the x-axis, we have the 12 months of the year, and on the y-axis, we have lapse rate in Kelvin per kilometer. Generally, higher or steeper lapse rates denote drier air, while lower or shallower lapse rates denote air that's more saturated. This plot shows an interesting bimodal distribution, but more interestingly, it shows that the period of greatest change between the decades occurred in the winter months. So this trended towards higher lapse rates during this part of the year, which is consistent with previous work that showed changing winters more over summers and elevation-dependent warming.
Our group is also interested in looking at precipitation over the Juneau Icefield, and specifically precipitation type. So in order to look at precipitation, we ended up taking precipitation data from the Juneau Airport and using that in combination with average icefield temperatures that were averaged from all of the camps to determine whether precipitation was falling in a solid or liquid form. And we looked at different seasons over time from 1986 to 2018. We defined winter as December through February, fall as September through November, and spring as March through May. We did not look at the summer because it was mostly liquid during that whole time period. So what this plot is showing is the percent of days with solid precipitation. So higher on the graph for a given season on a given year means that there was more snow that was falling, and lower indicates that there was more liquid precipitation that was falling. And we found that for each of the 3 seasons, there was a general downward trend. So the precipitation was trending towards a more liquid direction, with winter having the steepest trend towards liquid, and the spring trending below that 50% line in the middle. These trends were not very statistically significant, but they were interesting to note nonetheless.
Sorry. So far, we had defined summer as the classic calendar months, June, July, and August, but we wanted to come up with a new definition of ablation season based on what the glacier itself cares about. So we redefined the length of the ablation season at all camps from 88 to 2018 using climatological data to determine if ablation seasons were shifting over time. So we took a moving mean of temperature through time and created a threshold for how many days that mean needed to be above 0 to start the ablation season and below 0
to end the ablation season. We used a moving mean to smooth out noise from storms. On this graph, we've got year on the x-axis and length of ablation season in days on the y-axis. We've chosen to plot Camp 8 and 10 because while they are spatially close together, they are nearly a kilometer apart in elevation, and the elevation is listed down at the bottom. Despite the elevation change, we are seeing the same trend of no significant change in ablation season length over our time period.
The last factor that we evaluated was how long the ice field spent above freezing temperatures each year. And as part of this investigation, we observed trends in the number of days above 0 degrees Celsius within the fall and the spring seasons. So here we have the number of days with degrees above 0 for Camp 10, which is seen in red, and Camp 25, seen in blue, plot over time. And we chose to use these two camps to account for any potential influence of elevation because Camp 10 sits at the lowest elevation and Camp 25 sits at the highest. And here we see a positive trend in both of these two camps, which is suggesting that more days are becoming warmer in fall season. However, it's important to note that these were the only two camps where we saw statistically significant trends. And then this is the exact same plot as the previous slide, the same two camps, days per year above 0 over time. And this is for the spring season, March through May. And here we did not observe any statistically significant trends within any of the camps.
So for takeaways in future work, these are just some summarized bullet points. We found no long-term trends observed in days above defined temperatures. For camps 10 and 25, we found an upwards trend in positive degree days and more liquid precipitation in fall, winter, and spring. Investigating lapse rate, precipitation, ablation season, and positive degree days reinforced the past climate findings. This combined with the spatial complexity of the ice field, we believe calls for a higher resolution observational network in order to monitor future changes of the ice field more accurately. Thank you for your time. This is some contact information if you feel like getting in contact with any of us.
Great, thank you so much. That was another great presentation. Loving the clap emojis. Thanks, Team Climate. I think Team Isotope is up next, and we've got Team Bedrock Fractures on deck after that.
All right, hi everyone. We are the JERP Isotope team. All of our group members were able to be present today, and this is our project on isotope geochemistry of the Juneau Icefield. So water isotopes can be used as a proxy for temperature, which can be used to look into changes in variability of past climate. In this project, we focus on isotopes in delta notation, which describes the depletion of heavier isotopes in our sample, in this case in our ice cores, relative to the depletion of isotopes in standard ocean water. And this relative depletion of heavy isotopes serves as a proxy for temperature. And so we can look into this a little bit further using deuterium excess, which describes the depletion of deuterium relative to the depletion of O18. And this is important because it is sensitive to source conditions, such as evaporation set temperatures.
All right, so before we talk about our research on the Juneau Icefield, we want to talk about why this region is important in the first place. On this figure, all of the global isotope data is plotted. In light blue, there's data from surface samples all over Antarctica, and dark blue is data from the global network of isotopes in precipitation. And when we plot all the data collected on the Juneau Icefield since 2012, a very discernible gap is filled. Southeast Alaska is particularly relevant because the glaciers here are changing and retreating at the quickest rates globally, and are contributing the most to imminent sea level rise.
In 2019, a 300-meter deep ice core was drilled at the divide between the Mathis and Llewellyn glaciers. At its bottom, we estimate the ice to be between 150 and 300 years old. In that first 24 meters, we also know that a fern aquifer existed at the time the core was drilled. The fern aquifer acts very similarly to a groundwater aquifer, in which water is stored in the loose pore spaces between the snow. The 2019 ice core provides a record of oxygen 18, deuterium, and deuterium excess for the full 294 meter depth of the core. As we examine these records, we see increased variability in the top 24 meters of the core, overlapping with the Fern aquifer. This is particularly noticeable in the deuterium excess record plotted here. Let's go, next slide. The full deuterium excess record is shown with deuterium excess on the y-axis and the depth increasing to the right in the x-axis. Note the anomalous values seen in the top 24 meters. Understanding potential drivers of this variability has been the driving question behind our analysis.
So we can take this isotope data and input it into a simple water isotope model. And what we get out is this graph where we can see depth within the core on the x-axis, where 0 is the glacier's surface. And on the y-axis, we have condensation site temperature. And what we can see is that in that top 24 meters of the core, the variability in condensation site temperature falls pretty evenly within that normal range that we see throughout the rest of the core. But when we run this same sort of analysis for the evaporation source temperature, we can see that in that same 24 meters, the variability is actually pretty far outside of that normal range. And this is pretty interesting because it means that according to the model, something is changing at the evaporation site, and that is what's causing the variability in that top 24 meters. And this is something that we are hoping to look into more in the future, but at the moment, it's not our leading hypothesis. We think that this variability was likely caused by that Fern aquifer that we found in those top 24 meters, and that's what we spent our summer collecting samples to try and figure out.
So this summer, we continued a long-running effort to collect isotope data from across the Juneau Icefield. On this left figure, we've broken down where we collected those samples. We've got quite a range of locations, and we've collected them in three main techniques. One is doing surface transects to build a picture of how these isotopes change over space, and then we've also gone down into the snow with shallow ice cores and snow pits. On the right, we've plotted the oxygen 18 values for these different samples. And we see that we largely see what we expect. As you move further into the ice field away from the coast into higher, colder elevations, we get increasingly depleted oxygen values. So we've used some of this data to try to understand this question about the anomalies within the deeper ice core. One question we had was, could rainwater, we get a lot of rain during the summer on the ice field, so could rainwater be affecting our isotope values? And so we took a snow pit and we sampled it before and after a large rain event. And we found that in both oxygen 18 and deuterium, which is plotted here on the x-axis, we don't get major changes in the deuterium excess values before and after the rain event. We also wanted to consider whether meltwater could be impacting the deuterium excess values of our ice core. And so here we sampled two different locations with shallow ice cores, one which had an aquifer and a nearby site without an aquifer. We found consistently that the aquifer site had lower deuterium excess. We've also plotted the aquifer water itself here, which had higher deuterium excess values. Well, there are other potential drivers of this shift. For instance, these were sampled on different days, some difference in these sources, but we think this is an indication that the formation of an aquifer can alter the isotope profile of a site. So as we plot this data on a histogram, we see, as we expect, when we have an aquifer, the values are at lower deuterium excess values. And this is in those two shallow cores. When we plot our deeper ice core data, broken into less than 24 meters depth in orange, and then deeper data in blue, we see a similar profile. As we have an aquifer, we have values with lower deuterium excess values. The shift is slightly larger for the deep ice core, but we think this is potential evidence that the aquifer could be the driver of these strange deuterium excess values.
All right, so in the future, we hope to perform more back trajectories to prove whether evaporation source changes are responsible for these isotope value anomalies. We hope to drill some more shallow ice cores that have aquifers in them and compare those to our data so far. We hope to improve our depth age model because we've been using a relatively simple age model, and we want to get a better sense of the time period we're dealing with. And then we hope to drill a deep core in the future.
Great, thank you so much, Team Isotope. That was great. And thanks for including that contact information and awesome team photo in case people want to follow up with more questions as well. So we'll move swiftly onwards to our Bedrock fracture team, and then Team Iceflow should be on deck after them.
Great, I'll go ahead and share my screen. Cool. So thank you all for being here, and thank you, Alex, for the land acknowledgement at the beginning. As the title suggests, we're going to be presenting on bedrock fractures, and we're really interested in this because primarily of the way that they can influence downstream processes. And the way that they primarily influence downstream processes is by having different fracture orientations influencing the dominant erosional processes that occur when a glacier is interacting with the bed that underlies it. So as you can see in the top row of this figure, there are parallel fractures to the direction of flow, meaning that the dominant erosional process would be abrasion, resulting in these smaller particles that result in more turbid water or cloudier water downstream. In contrast, if the dominant fracture orientation is perpendicular to glacial flow, then the dominant erosional processes will be much larger. So we're thinking about processes like plucking and quarrying that result in big particles that cause much less turbid water downstream. And so we're really trying to contribute to this body of knowledge about subglacial bedrock fracture density and orientation. That's kind of the science question, but we are also thinking about a process question as well. And that's what methods can be used to study bedrock fractures. And the one that we were really interested in thinking about was something called structure for motion, which Max can discuss.
Yeah, so we made models, 3D models of these bedrock outcroppings by flying around a commercially available DJI Phantom 4 drone around the bedrock outcropping, taking photos as we went. Then we georeferenced these photos with ground control points, which we got GPS points from these Amplitude Reach GPS units. And then we took all those images and GPS points and spliced them together to create our accurate 3D model, which we use a program called Agisoft Metashape to do that. Then we post-processed our data and tried to get some meaningful insights about the fracture density and orientation. Next slide. So on the left, we have the larger photo of the Juneau Icefield with a 10-mile scale bar there. And on the right, we have a zoomed in area on the Echo Glacier where we did our flights. And we show, we have the first area here, Echo North, and the next area, Echo Mountain, and then the last area, Echo Terminus. So these are the 3D models we created. And we chose these sites because they all have the same bedrock type, the granodiorite. And if you hold this lithology constant, there's only two other factors that really have a dominant role in the erosive process. So that's the bedrock fracture and the orientation. So by having the same bedrock lithology, we were able to just study the variation between those two things.
Great, so we started off with the grayscale image. So I believe this one was from a cloudy day. And then we edge detected the image to give us the image on the right. And then we put this image through a script that was in large part written by previous JERP student Colby Rand. And now that we've done this, we can kind of see the more damaged areas or areas that have a higher density of fractures. And those are going to be in red and then kind of like orange. And then the less damaged areas are kind of the blue ones, and they have a lower density of fractures. We also get that histogram to the right, which shows us the fracture orientation. So in this case, it's mostly, you can see it's kind of around 90, which checks out with the image that was used in this example. where you can see the fractures are mostly running up and down.
We ran into a couple of problems in this work, and we ultimately asked more questions than we answered. The first thing that we have to do going forward is figure out how to clear off rubble from the images we're working with. At the outcrop scale, we weren't able to run the analyses that we needed to because rubble gets picked up, the edges of rubble gets picked up by these scripts and by these grayscale images as fractures, which throws off our data. Once we move past that rubble clearing, we actually have to be able to apply the interpretation of fractures, density, and orientations that we see on marginal outcrops subglacially. That is to say, we have to project the data, we have to project the results we receive to the subglacial in order to better quantify what these erosional processes are actually looking like. That's probably a process that's going to require machine learning. The other thing that we also have to incorporate is how the mass of a glacial body, particularly in a valley, creates its own extensional fracture subglacially instead of just the fractures that are present on the marginal outcrops being extended subglacially. So there's a lot of questions that we still have to answer. There's a lot of work that we still have to do, but it's a promising technique going forward to try and help create a better model of a control on glacial erosion. And that's us.
Great, thank you so much. So we've got our next team up is Team Iceflow, and our final team should be on deck, Team Crevasse. So Team Iceflow, take it away.
Hello, my name is Anne Randall, and I'm presenting with Mark Cahalan on ice flow velocities on the Juneau Icefield in Juneau, Alaska. So our work focused on validating Sentinel-1 microwave SAR glacier velocity tracking and its accuracy on temperate glaciers. Our area of study was a historic profile on the Taku Glacier, a temperate alpine glacier located on the Juneau Icefield, and this transect is referred to as Profile 4. For our field data, we gathered the assessed ice flow by measuring the displacement of the velocity stakes that we placed on the Taku Glacier corresponding with the Sentinel-1B flyover dates. We then transferred the data that we collected from the RTK GPS for stake positions and input the data into ArcGIS to calculate the velocity and displacement of the stakes. We utilized the data collected by the European Space Agency's Sentinel-1B satellite, which used microwave backscatter to image the terrain, which pierces through cloud cover, making it ideal for tracking ice flow velocity in regions with frequent storms and heavy cloud cover. In the processing stage of our data analysis, we applied the orbit files to the SNAP application, the Sentinel image analysis platform created by the European Space Agency, in order to co-register the images, apply offset tracking, and terrain correct the image files. So we placed our stakes on July 7th on the Taku Glacier and revisited the sites on the 18th, which corresponds with the Sentinel-1B flyover dates on July 6th and 18th. And we used the MLID Reach RS2 real-time kinematic global positioning system, which has a 1 centimeter accuracy and consists of a base station and a rover, and connects to the Reach View 3 application used on a phone in order to establish the starting and ending points for measuring the velocity of the stakes. Sentinel-1 consists of 2 satellites, Sentinel-1A and 1B, which provide microwave backscatter imaging of the terrain, and each pixel in the image produced by Sentinel represents an area of land that is 10 meters by 10 meters, and we revisited the sites 12 days apart, contemporaneous with the Sentinel-1B flyover dates.
Here we see the results of our GPS field measurements along Profile 4 on the Taku Glacier. We see flow into and out of the main glacier on the margins and terminus directed flow towards the southeast with increasing magnitudes into the center of the flow line, as we would really expect in a nearly 1,500 meter thick valley glacier. Here is the comparison of our GPS measurements and the Sentinel-1 measurements. On the left, our GPS offsets are shown again with these red arrows in red gradients, and using a GIS inverse distance weighting tool to interpolate and extrapolate speeds for visualization purposes around it. You'll note the scale down here from 0 to 0.8 meters per day. On the right is the offset tracking velocity field for Sentinel-1, requiring an internal correlation greater than 0.5 for the co-registered image pairs to recognize movement in SNAP. And you'll note the very heterogeneous distribution of velocity magnitudes across the whole width of the Taku. By running a nearest neighbor correlation between the stakes and the Sentinel velocity field, we find a statistically significant, with a p-value of 0.00049, poorly correlated inverse relation between the in situ and satellite measurements. So to understand why we have such a poor correlation, we're going to look at the before and after Sentinel images. Here are the raw Sentinel-1 microwave backscatter images. Profile 4 is highlighted. Raw images are in fact flipped. So you'll notice the Taku flowing towards the bottom left, which is southeast. During our observation period, we were caught in a week-long summer storm. The additional rainwater saturated the snow, and diurnal freeze-thaw cycles caused ice lensing within the top about ½ meter of snowpack, where microwaves can penetrate. This clearly impacted the microwave scattering, as you can see from these arrows in the before and after, lowering much of the pixel-to-pixel correlation between our threshold requirements on SNAP offset tracking. This whole situation may be an outlier, or it may show the trend of uncertainty in tracking ice velocity near the phase transition. Our initial findings then, while inconclusive, show that Sentinel-1 offset is not necessarily dependable as a method for measuring temperate glacier velocity. However, we've already started on follow-up work. Frederick Alexander University in Germany has a supercomputer using speckle and offset tracking methods to determine worldwide glacier velocities from Sentinel-1. Here is an example comparing our profile for in situ data to the FAU data set. Despite the higher constraints used on the FAU velocity data, nearest neighbor analysis shows a statistically insignificant, very insignificant, completely non-correlated relation. So to quantify uncertainty, the uncertainty distribution of Sentinel-1 derived glacier velocities in temperate regions, we're going to expand our work to 22 additional velocity stake profiles across the Juneau Icefield, where measurements are recorded from 1993 to present by Scott McGee, who is here. And we're going to compare these ground data to Sentinel-1A and Sentinel-1B velocity tracking from their respective launches in 2014, 2016 until present. I guess we will be doing questions at the end. Here is our contact information, and thank you very much.
Great, thank you so much. And last but not least, we have Team Crevasse up. So please go ahead.
All righty, I'll go and share the screen. Okay, can you all see that?
That's great. Awesome. We are the Crevasse research team, and this summer we did fieldwork on the Von Lewis icefall to better understand the fracture mechanics of ice through local observation. So our driving research question was, how do we measure crevasse geometry and strain in the field? And through doing so, we hope to develop and improve upon existing methods of measuring fracture. The significance of this being its ability to be scaled up towards regular monitoring of fracture on temperate glaciers, and then further implications of relating localized field work and collecting data to remotely sensed observations. So the first data we collected was we did a local strain survey using 5 velocity markers, measuring the relative displacement using RTK GPS, which you can see Scott using in the left image. And with the strain rates collected on the right, you can see a figure where we plotted the principal strain axes, red representing the most tensile strain rates and blue representing the least tensile or compressive stress or strain. And 2 noticeable trends we wanted to point out was you can see the greatest strain rates found in the along flow direction, and there's a present strain gradient from the top of our field site to the bottom, which is contrary to our assumptions based off of surface expression and observations made while navigating the field area.
So a big part of this project involved developing field methods for measuring crevasse geometries since they've rarely been measured. And we started measuring depth by using a plumb bob line held over the edge of a crevasse, which you can see in the top left image. However, this presented some issues as the plumb bob would sometimes get stuck on the edges of the crevasse, preventing it from measuring the deepest point. And we were limited to only measuring crevasses whose edges are safely accessible, which excludes most of the crevasses in the icefall. So to try to address these issues, we started carrying a ladder into the icefall, which we laid across the crevasse, which we can see in the bottom images. And then we could throw the plumb bob over the center rung of the ladder so that it would reach the deepest point of the crevasse while also allowing us to stay further from the edge. And then we measured our plumb bob line back in camp with a measuring tape. So these techniques produce the results that are shown here with the first and fourth crevasses, which we can see their locations on the field site map on the right, were both measured near the edges. So those depths reported are not necessarily indicative of the maximum depth. Most notably, the deepest crevasse we measured was deeper than the length of the bob line, which was about 50 meters.
So while we were interested in looking at in measuring crevasses in a local area, we also were interested in looking at how these crevasses are interrelated within a larger feature, such as this icefall. And so what we decided to do, since we can't sort of measure all the crevasses in this large area, is we decided to take some drone imagery. So we had a drone with a high resolution camera, and we took hundreds of photos of the icefall. We stitched them together using using an orthorectifying program, and the result of which you can see here. This is a stitched together picture of the Von Lewis icefall. And to give some people some orientation, on the left over here is the beginning of the Gilkey Trench. If you haven't seen the Gilkey Trench before, I encourage you to look it up. It's quite a stunning feature. And for those that have been here, up at the top left, you can actually see a little bit of a bird's eye view of Camp 18, just to give you a pretty incredible scale of this place. And this is another reason all the blue area is sort of where the crevasses have fractured and have been damaged. And so it's quite unsafe for us to travel all the way down into these very damaged areas. Our research site was further up in the top left here. And so to measure the icefall as a whole, we decided to implement an algorithm, a computer program that we called the damage density program, which essentially takes the photo you just saw and turns it into a black and white photo using some threshold that we determined earlier. And then we cut up the image into a bunch of little squares. And then you take the ratio of the black pixels, which we call the damaged pixels, over the total pixels. And that gives you the graph on the right, which is the damage density profile of the Von Lewis. And as you can see here, there's some interesting patterns. One that's unsurprising is that, from the top of the icefall down, as the colors get darker, it becomes more damaged. That makes sense that things are getting more damaged, but you can also look laterally, things are becoming damaged off to the sides. And so in the future, we're looking to analyze this further. In regards to other future work, let's see. From the local point of view, we want to see how our field data compares to the current models, given the Nye model for fracturing, and also the LEFM, the linear elastic fracture mechanic model for strain rate models. We're also interested in how our local ground strain rate measurements compare to the satellite data that's available. And along the lines of satellite data, we want to look at how our density profiles compare to satellite collected velocity data to see if there's a relationship there, because if one can understand the strain state using this damage density profile, perhaps we can look at crevasses and icefalls in a perhaps new way. And with that concludes our presentation. And here's our contact information on this page. Thank you all.
Thank you, everyone, and thank you to all of the students for some great presentations and also sticking to time, so we actually have time for questions for everybody now. So if you have questions, feel free to either say it in the chat and we can call on you, or you can use the raise hand feature and I can call on you to turn on your microphone and ask your question. And I see that we have some really positive comments. Thank you, Roger. Thank you, Celie, for comments in the chat. So students, make sure also, Drippers, make sure you're reading the chat comments as well. Who wants to be the first question asker? Please raise your hand or comment in the chat. Or I have a couple, but I get to ask anytime I want, so I don't want to monopolize it. Ooh, we have one raised hand. Roger, go ahead.
Thanks very much, Alan, and thanks once again to all the speakers. That was just awesome, really good. My questions to the GPR team who were on first. I see your to-do list has encumbered a future group with both multi-offset and CMP radar. So I hope they'll still talk to you once they've finished with the effort of doing both. I wonder if you thought each of those was going to deliver something different and unique. I mean, they can both get you a velocity estimate using normal processing techniques, but I wonder why you plan to do both. Thanks very much.
Thank you so much for that question. So I think the methodology or the thought behind doing multiple of these is, from my understanding, the common midpoint survey is more of like in separate discrete points, but the multi-offset radar could be moved along a line transect. And so what we were seeing in the data that we collected this summer was a spatial variability in the relative permittivity calculations. And so I think doing both of those might have a benefit of having like, instead of just a few point measurements, having a continuous line of measurements. I'm not sure how to individually or as a team interpret this data yet, but hopefully learning that will have more information there. So I hope that answered your question.
Yeah, that's smashing. Thanks very much, and good luck to you. Cheers.
Thanks. Tavi, I see you have a question for Team AP-Res.
Yeah, just to throw something to the radar team, actually, after Roger's question there. Have you also thought about doing multipolarized radar if you wish to inflict even more pain on future students? So where you have antennas, you know, in different orientations, so all the standard ways that you can use antennas that can tell you about the orientation of water bodies in the ice, for example.
Wow, that would be really cool. It does sound like maybe it's very labor intensive.
It is, yes.
But that's not something that we've discussed, but it could be a very interesting opportunity given the different water bodies and fern aquifers that we know exist on the Juneau Icefield. So thank you for that.
The question I had for the AP-Res team was more, I've been struggling for a little while to get my head around quite what information AP-Res might usefully give us from valley glaciers. And I wondered what you thought the best case scenario is. You know, what should we be able to get from AP-Res data on these warm, melting glaciers where we're not really that interested in the melt rate? Because of course on ice shelves, it's the melt rate that you're most interested in. So that makes it easy to use AP-Res. Anyway, I'm still trying to get my head around it, and I wondered what you guys thought about that.
So my understanding is that AP-Res gives the ability to, for one, have like a really good autonomous way where we can leave it out in the field and just have set constraints for how we're measuring. But the actual reason, the advantage of the AP-Res, we're able to measure, or theoretically you're able to measure the strain rate, or so if we have any type of lifting of the if you're having water content, subglacial water content, there could be some internal deformation lifting up the glacier above from the increased water pressure. So you'd have the ability to constrain, like on very more finite detail, the the layer migration and the shifts within the glacier. But as far as being in the temperate region, we really weren't sure how readable the results would be. I know the unit's been used previously on the Juneau Icefield a couple years ago, but my understanding is that the results were liminally processed, and I'm still working on going through the preliminary stages of trying to find out what looks good and getting a good average for if there's any long-term patterns versus just diurnal processes. So that's as much probably as info as I could give you right now.
I wonder too as whether you can see if a piezometric surface in the glacier is changing. So sometimes if you get diurnal water pressure signals, you actually get essentially a piezometric surface. Yeah, it's really interesting. Thank you very much.
Great. Thank you so much, everyone, for attending, for the great presentations and the questions. I know we're at time, so I want to be respectful of that. And just remind everyone that applications are open for students and faculty and different types of involvement. If you want to talk more to Seth or Annie about how JERP might fit in, say, your broader impacts of future grants, please do so. And then, Tavy, I want to hand it back to you because I think you have one more thing you might want to do to finish off the session, perhaps after turning off the recording.
Oh, that's an interesting point.